So the conditional probability of event A, given that we know that B has already occurred, is the same as the probability of A computed in the restricted sample space B. You must be thinking, now that I have understood conditional probability, I must be close to becoming a data scientist. You might be thinking that probability of me becoming a data scientist, given that I know conditional probability, is greater than the probability of me becoming a data scientist in general. But is it true? What if I tell you that when you started this journey, your probability of becoming data scientist was, let's say, 0.5. Now that you have learned all this stuff about probability, your probability of becoming data scientist is still 0.5, because the success in data science does not depend on whether or not you understand probability. It actually depends on whether you understand statistical independence. So what is statistical independence? Two events A and B are said to be statistically independent if P of A given B equals P of A. Let that sink in. I'm going to give you 10 seconds. P of A given B equals P of A. This is sometimes also called stochastic independence. Now, a lot of people get this wrong. Some think that statistical independence means P of A given B equals 0. No, this is called mutual exclusivity or disjoint. Let us understand from the Venn diagram. Suppose P of A equals 0.4 and P of B equals 0.6 and P of A intersection B equals 0.24. What is P of A given B? It is P of A intersection B by P of B, that equals 0.24 by 0.6, that equals 0.4. This is exactly equal to P of A. Therefore, A and B are statistically independent. Notice that P of A intersection B equals P of A given B into P of B. So, if they are independent, then P of A intersection B equals P of A into P of B. Sometimes this is also used as the definition of statistical independence. We are going to dig deeper with the help of some examples. Consider the experiment of drawing a card from a deck of cards. Let A be the event, the card is an ace. Let B be the event, the card is a spade. So if you know that the card is a spade, does that change the probability of the card being an ace? Let's see. There are 4 aces in a deck, so P of A equals 4 by 52, that equals 1 by 13. There are 13 spades in a deck and one of them is an ace. So if the drawn card is a spade, then P of A given B equals 1 by 13, which is the same as P of A. So these events are independent. Now let's make this interesting. Suppose a white die and a red die are rolled together. Let A be the event, the white die turned 4. Let B be the event, the sum of the faces of the two dice equals 7. Take a moment to think about it. Are they independent or dependent? You might think, well, 4 plus 3 equals 7. So if I know that the white die showed up 4, the event of the sum of the two die becoming 7 must be dependent on the first event. Let's see. First of all, P of A equals 1 by 6. Let us see all the different ways in which the sums can be 7. They are 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, 6, 1. There are 36 possible combinations overall, so P of B equals 6 by 36, that equals 1 by 6. What is P of B given A? We can see there is only one case where the white die turns a 4 and the sum equals 7. So P of B given A equals 1 by 6. That equals P of B. So these events are also statistically independent. Suppose there is a family with 3 children. Let A be the event. The family has children from both genders. Let B be the event. The family has at most one girl. You might be thinking, no way these two events are independent. Surely, if I know that the family has children from both genders, it definitely increases the probability of having at most one girl. Makes sense? Let's check the sample space. It is GGG, GGB, GBG, GBB, BGG, BGB, BBG, and BBB. If you exclude the first and the last outcomes, 6 are favorable to event A. So P of A equals 6 by 8, that is 3 by 4. What about B? At most one girl. So the favorable cases are GBB, BGB, BBG, and BBB. So P of B equals 4 by 8, that equals 1 by 2. Now what about both of these events occurring together? There are 3 favorable cases, GBB, BGB, and BBG. So P of A intersection B equals 3 by 8. But this is equal to 3 by 4 into 1 by 2. That equals P of A into P of B. So these events are statistically independent. What's the moral of the story? Do not confuse physical independence with statistical independence. Like I've said before, intuitions can get you in trouble on the streets of data science. So it is always good to double check. You have learned one of the most important concepts on which the field of statistics is based. A large part of statistics deals with checking whether two things are independent or not. We are one more step closer to the destination, but the saga continues. Want to continue the journey? Then subscribe and like. Probably the most famous theorem in the field of probability is the Base Theorem.